Hey guys, BuildZoid here, and today we're going to be taking a look at the XFX RX 590 Fatboy. The photo of the GPU is, of course, from Tech PowerUp, so huge thanks to them for providing high-resolution PCB images like this. I'll leave a link to their review of the card down in the description below. It's like, I actually like their reviews, so you should probably check it out. Anyway, today we're just going to be looking at the PCB, and as usual for me, so let's get right into it. So the first thing I want to highlight is this card does have a BIOS switch, and it does have dual BIOS, which is always a nice feature to have, especially on AMD Polaris cards, because you can actually you can still mod the BIOSes on these. You can't mod BIOSes on Vega, but you can mod the BIOS on these. So you can remove things like, you can do things like remove your power limit, adjust your voltages, run better memory timings. I know AMD recently put out a driver update which added some memory timing presets to the driver, but I'm pretty sure manual custom BIOS timings are still going to be faster than whatever presets AMD put into the driver, just because I'm guessing that they're being awfully safe with the presets that they put into the driver, compared to what you can do when, you know, there's nothing stopping you from just doing whatever the hell you want to the timings. Anyway, so yeah, the dual BIOS switch does come in really handy in case you screw up and somehow break the card. So that's nice to have. Also, this card is does have an extra 6-pin. Well, it's not really extra. It has a 6-pin power connector and an 8-pin power connector. And I think so. I have an RX 580 Red Devil from Power Color, and the interesting thing about that card is that basically the 6-pin and the 8-pin on that card are in parallel. It doesn't really they're on the same 12-volt power plane. So there's no difference with having the 6-pin plugged in or not. At least if I remember correctly. Here, we can actually clearly see that XFX has the 6-pin powering some stuff and the 8-pin powering some stuff. So we can clearly see that we have this input filtering choke right here, and then we have this other input filtering choke. And, well, this one's really obvious. That goes to the high side MOSFET of our memory power right here. So that's Vmem. Bam. And then this right here, well, there's a bunch of vias, and then it goes into the board and comes out somewhere in this area. So I'm going to say that the 6-pin probably feeds this group of phases down here, because you can just about, can you see it? You can just about make out the PCB separate, like the power plane separation right there. So that's very likely going to be, and you can also make it, just about make it out down here. So that's very likely feeding this, and this power stage of the Vcore VRM, which we have here. So that's your Vcore. This little regulator down here is, of course, the 0.9, well, it's not 0.95 volts. We'll just call it VDISP, so display drive voltage. This voltage is sometimes helpful with AMD cards if you have issues with black screens on liquid nitrogen. Otherwise, you can just ignore it. It's also a really good way to break your GPU. If you raise this voltage too high, it kills the memory, it kills the display output circuit, and yeah, the card's dead. It can actually do more damage than just that. You can very easily just destroy a card with that voltage. So generally speaking, you do not touch that unless you have problems that you need to fix. Up here, we actually have another regulator, and I'm not sure what that one's for. Below that, well, I have a suspicion of what it's for, but I'm not 100% certain. Under that, we have the what is called a VDDCI, or aux, as some programs will call it. So auxiliary voltage. So that's this rail, right? That's that VRM right here. Now the 6-pin, right? If we look over where the 6-pin is, that one goes into this big pad over here, and then we have a bunch of vias in that, and it drops into the ground, drops into the PCB, and then it goes somewhere. And I think it comes out right here, and it powers these two power stages. So you have 2 of these power stages on the 6-pin. Then you have 3 of them on the 8-pin, and I'm really, I'm a fan of this memory, this assignment. I'm a big fan of that. And then finally, VDDCI and this one phase of Vcore is on the PCIe slot. I'm a big fan of that. I think this is a really good way to hook up your RX 590 power. If this is actually how it's laid out, I'm a big fan of it. because this is very sensible, right? Half the Vcore VRM is going to be pulling off of the strongest power connector the GPU has, which is the 8-pin. Then the 6-pin power connector is going to feed 2 more Vcore phases. And then we put a single phase of Vcore onto the PCIe slot. This basically just ensures that you can still turn the GPU on if you forget to plug in these power connectors, right? If these aren't plugged in and none of these phases were on the PCIe slot, like if you tried to turn the card on without the power connectors, the card would just not initialize because there would be nothing to power the core. So yeah, here they have one phase of Vcore on the PCIe, and they also have the VDDCI, which this is a minor rail. It barely pulls any power, so you don't have to worry about that. And Vmem is also on the 8-pin, which, again, it doesn't really pull any power. You don't need to worry about that. So, yeah, I'm a big fan of this power distribution that XFX is going for here. Like, I think this is a good way to do it. If you're gonna have a 6-pin and an 8-pin, this is the way to wire them up. Assuming I'm actually correct about the arrangement. They might have the 6-pin and the 8-pin swapped around. So I think this is the 6 and that's the 8, right? So anyway, that's that. And so if we go to the back of the card, and right, GIMP's being GIMP, so this now works again. So on the back of the card, we have this voltage. This is a integrated buck converter. This might be putting out 5 volts. It might be putting out 7 volts. I'm not sure. Yeah, that's actually... because it also goes past the legs of this low dropout regulator. Like, well, this would... I assume this would be a low dropout regulator if it was there. There's also this chip right here, which is very... Is it? I'm not sure if I'm misreading that U label. Let's find a discrete transistor somewhere. This is a... No, that's MQ. Okay, Q is transistor on here, so... Yeah, this is very likely an LDO as well. So this might be 7 volts. I'm not sure, again. So the thing is, why I'm looking for the 7 volts or 5 volts is, and GIMP being GIMP, where's my mouse? There's my mouse. So the thing about the 5 volts and 7 volts is, of course, these are power stages from International Rectifier, right? And they don't run on 3.3 volts or 12 volts. No, they run on 5 to 7 volts. At least, well, they're not... Apparently, they have reliability issues on 7 volts, but I don't... Like, the data sheet is spec'd in 7 volts. I don't know the details of it. I think it might also it might also depend on like design implementation specifics or something like that. So like, I guess XFX might be able to run them on 7 volts or something. So anyway, they just don't run on 3.3 volts or 12 volts. So these need 5 volts to 7 volts to function. And the thing about that is, well, you don't get that from the PCIe slot. So you do need a voltage regulator to produce that. And the one up in the... This is going to get really old really fast. The one up here, or this one down here, is going to be doing that, and powering them. And like, I really wish I had the card just so I could check what it's actually outputting, because if it's on 7 volts, then this VRM is going to be quite a bit more efficient than if it's on 5 volts. It might also like not be reliable, but while it works, it'll be more efficient, which kind of interesting situation. So yeah, I'm not sure about the... Like, the thing is I'm just going off of information I got from Gigabyte, and they were like, oh yeah, they use a bunch of International Rectifier parts that are, that also have their data sheets written entirely in 7 volts, and then I was like, so, what'd you run them on? And Gigabyte was like, oh yeah, we run them on 5, and I'm like, could you not run them on 7 for better efficiency? And they're like, nah, they say, apparently they don't work. Apparently there's reliability issues at that point, and it's just like, okay, well, that's odd. But anyway... yeah, so that's the situation with the 5 volts to 7 volts here. Now then, let's take a closer look. Well, now let's actually focus on the Vcore VRM proper, right? So Vcore VRM is a 1, 2, 3, 4, 5, 6 phase, and this is controlled by this chip over here, which is the IR35217. This is kind of new. Normally on like RX 480s and RX 580s, you'd find a 3567B. And the 35217 is actually new and came out with RX Vega. Well, no, Vega Frontier Edition. Like, this is a new chip for Vegas. So I assume it supports some, but I'm not sure that the RX 590 actually needs it. Like, I assume for Vega, it supports some extra power management stuff, but for RX 590s, that very likely isn't a thing. So yeah, I'm not sure, like, especially considering that there are RX 590s using NCP 81022 controllers, and those things are dumb as bricks. So, well, not dumb as bricks, but a lot dumber than like a 3567B is. So, yeah, it's like, yeah, it's kind of interesting that XFX is opting for this controller. I guess they have a bunch of them left over from like RX Vegas or something. Like, I can't really, like, I don't think it's necessary to use this chip here. It might also be that this one's getting discontinued or something like that. So, yeah. Anyway, it's a really nice high-end voltage controller. Unfortunately, there's no full data sheet. There's no public data sheet for it. So that does kind of suck. But it does support 8 phases, up to 8 phase configurations. And it's been, like, I've seen, like, you can do a 6+2 off of it. You can also do a 7+1. I'm not sure that it can run an 8+0. I'm not sure about that. It might be able to do that just because that would be really similar to a 35201. But I'm not 100% certain. Anyway, here it is running, of course, as a 6+1 because it also takes care of this phase up here, which is the 1 phase of VDDCI. So, yeah, control-wise, you know, nothing super complicated. It's just a straight 6 phase. That's nice, nice to see. The actual power stages themselves right here are international rectifier parts, of course. International rectifier controller, international rectifier power stages. That's just kind of how that works. You get IR 3578s. And so these are kind of special. So these are what are known as exposed exposed top power IR stages. They're rated for 50 amps maximum continuous output. And this metal tab is really cool. Quite literally. Well, actually, no. Literally, it's very hot because it's directly connected to the silicon inside the power stage. And essentially, the idea behind these is you can massively reduce the thermal resistance of the packaging of the chip. So normally, if you attach a thermocouple right on top of one of these power stages, the thermal resistance of that power stage is 7. Like, I think I pulled that, yeah, from a 3551 data sheet is where I pulled the figure from. So on a 3551, which is basically, like, that's also a 50 amp power stage. It's slightly older than the 3578. Main difference being the switching frequency tolerances. But anyway, so, like, well, power efficiency at high switching frequencies. But anyway, it's also a 50 amp power stage, and that thing doesn't have the exposed metal top. And that one has a thermal resistance to the top of the top of the package, right? So if you put like a thermocouple right in the middle of it, that temperature that you're going to measure right there is going to be 17.5 watts. 17.5 degrees per watt lower than what the internal temperature of the power stage is. So if you put a thermocouple on top of the power stage, right, on top of a 3551, and the 3551 is producing, let's say, 2 watts of heat, and you measure the top of the power stage to be at 100 degrees Celsius, then the internals of the power stage are at like 135 degrees, right? Because they're 17.5 times 2, higher. Is it 35? Yeah, it's about 35. So 135 degrees Celsius internal when you measure 100 on top. With this, the thermal resistance is 0.5 watts. Degrees per watt. So essentially, what you measure on this metal pad is what the temperature inside is, right? Like, even if one of these was producing 10 watts of heat, the difference is going to be 5 degrees between this metal tab and the actual junction inside the MOSFETs. So that is really, really cool. It basically means that these are really good at dumping their heat into heat sinks. And that's why, you know, that's what makes them kind of special. It's also more expensive to manufacture power stages like this. So it is it's a cool thing, but it is expensive to do. And yeah, it gets hot. Literally, like, because it's directly connected to the hottest part of the, like, to the MOSFET, it does actually get hot, but it's a cooling thing. So it's cool in that sense. Anyway, the other thing you need to know about this metal drain is that it's actually connected to the switch node of the power of the MOSFETs. So basically, you're gonna get a nice like this. This is gonna sit at plus 12 volts a good chunk of the time, which means you really do not want to like try any kind of direct contact to these plates. Okay, because if you do, like, if you connect this plate to that plate, you're gonna have a really bad day. Okay, like a really, really bad day, because those are separate phases. Like, it's very likely going to just break the card. So they can be short-circuited, and that is something worth noting. But cooling-wise, they're really, really cool. So, yeah, that's neat. And the end result for this VRM's efficiency is that pushing 1.2 volts, so 1.2 volts out, at 400 kilohertz switching frequency. And I've decided to spec both because I don't know what the card runs on. 5 volts or 7 volts drive. You're going to be looking at the following VRM heat output. So at 150 amps output, it's going to produce 18 watts at 5 volts drive, while it's only going to produce about 15.5 watts on 7 volts drive. So this is why I really hope this is running it on like 7 volts or even 6. Like, the thing is, the efficiency curve for these things with drive voltage looks like this. So that's 5 volts, that's 7. If you run on 6, it's actually still pretty, like, it's pretty close to the efficiency of 7 volts. So yeah. Anyway, but I don't know what the card actually runs on, which is why I'm putting both. Anyway, so 200 amps, which this is easy to hit. On like a RX 580, you can hit 200 amps no problem. So on a 590, which these tend to clock a bit higher, they're all also on the 12 nanometer process from GlowFlow, which this is the same process difference. At like, essentially, this is kind of like, I've seen a lot of people call the RX 590 a rebrand of the 580, but that's like really, like, compared to like a 580 versus RX 480 difference, that's actually really incorrect. Because the difference between a 590 and a 580 is basically the same as the difference between a 2700X and an 1800X Ryzen CPU. As in, the 1800X was made on 14 nanometer GlowFlow, and the 2700X was built on 12 nanometer GlowFlow. The RX 590 is the same thing. The die is still the same size, and that is also true on Ryzen, where basically the difference with the 12 nanometer process is they've not actually made the dies smaller, they've just made the transistors smaller. And the end result is the transistors clock a bit higher, but they're a bit less, like, for a lower voltage, they clock higher, but they leak more power. So once you crank up the voltage, they end up being actually not that, like, they end up pulling more power, but they also still clock higher. So the 12 nanometer process is basically like the high performance variant of 14 nanometers. It's not really any denser, especially because AMD doesn't want to relay out their chips. Like, that's the other thing, is like, yes, they could have made the 12 nanometer stuff smaller, but they've basically just gone and taken the 14, like, because it's so similar to 14 nanometer, it's just easier to just take the 14 nanometer layouts and run those. And the end result is the die's the same size, but it clocks higher. So that's the difference with 12 nanometer. However, it also will, for a given voltage, pull more current. So that 200 amps figure, very likely that you're going to be able to hit that on a, especially if you're overclocking and destroy all your, like, remove all your power limits, start raising the voltage, you should have no problem hitting that. And at that point, the VRM is going to be producing about 29 watts of heat while driven with 5 volts versus about 25 watts of heat when driven with 7 volts. Now, going up further, 250 amps, which we're starting to approach the limits of this VRM, so the VRM heat output is about to get kind of silly. At this point, it's going to produce about 44 watts of heat at 5 volts drive and about 38.5 watts at 7 volts drive. 300 amps output, you're going to be looking at 65.5 watts of heat, which actually that's kind of irrelevant at that point. But and about 56.5 watts of heat on 7 volts drive. So yeah, you can see, especially at like the higher currents up here, which this would be like pretty extreme. Like you'd have to be pushing like pretty heavy overclocks, high voltage on like water cooling, dry ice, liquid nitrogen, that kind of thing. You might be hitting these kinds of current figures at that point. Well, dry ice would actually reduce the leakage problem. That'd actually be an interesting comparison. How temperature sensitive is 12 nanometer versus 14 nanometer in terms of current draw? That would be an interesting test, especially at higher voltage. Because at higher voltage, the leakage is higher, so there'd be more potential. Like there'd be more of a problem to fix with the reduced temperatures. But anyway, yeah, like if you're on water cooling, you should still be able to hit at least 250 amps. I mean, what did I do? I was burning a lot of power on an RX 480. So this should be able to burn even more than a 480, no problem. Assuming it scales with voltage. If it doesn't scale, then yeah, it might actually not. It might not be quite as bad. Anyway, so yeah, VRM like the actual figures for the VRM. Honestly, this is not the most efficient VRM to ever be on an RX 590. However, just because these chips have that exposed drain, they don't need to be as efficient in order to still maintain like good temperatures, right? So they have a huge cooling advantage over a lot of the competition, which means, yeah, like even if this was driven on 5 volts, like this is not a bad VRM as long as you have a heatsink on it, right? And actually, it's also worth noting that even if you didn't have a heatsink on it, you do kind of... There's a lot of space back here that's literally just power plane, and if you have if you forced a good amount of airflow through this area, this should have no problem. Well, not no problem, but it should be able to get rid of quite a lot of heat, depending on how much airflow you throw at it. So, yeah, I rather like this VRM. I think since they are, like, it would have been cool since they are using a 35217, that if they could have gone to like a 7+1. Also, instead of a 3578, they could have gone for like a 3575. But, like, you know, every upgrade you make to the card is going to just add cost. So I can totally understand that they wanted to keep it on this, right? Like, it is a RX 590. Like, this thing can't be ridiculously expensive. But, yeah, like, it's a solid PCB. It's not it's not the most efficient, but definitely this is it's a solid VRM. It shouldn't really have any cooling issues. And power delivery wise, it should be doing great. Also, you can crank up the switching frequency on these things to like you could go up to a megahertz switching frequency on these chips, which may or may not improve overclocking. It would definitely make your efficiency even worse. But so yeah, but at that point, like that happens regardless of what chip you're using, and at that point, the exposed drain might actually be quite a significant advantage. So yeah, I rather like the PCB here. Like the VRM on this, and the PCB too. I mean, it's not bad. There's some nice features on it elsewhere. So. Yeah, that's the Vcore VRM. VDDCI is another 3578, which is like, basically, let's do it this way. 20 amps VDDCI output, which I think is more than what the VDDCI will normally push anyway, is going to be 2.5 watts of heat. And 30 amps output, which should be way beyond what that rail will normally push, will be about 4 watts of heat. So you don't need to worry about it. Right, this is going to be just fine. So, yeah, the main concern is, as usual, just the Vcore VRM, because that's going to produce most of the heat. And yeah, and then for memory power, we have the same VRM that they've used on the RX 580s that XFX has used, and that is 1 high side MOSFET, 2 low sides, and you basically get a Sinopower SM. Is it? No, I think it's SM for their part number. Some idiot screwed up my notes. Well, more like some idiot copy-pasted his notes and then didn't update them. Anyway, it's a 4377. If you look up Sinopower 4377 MOSFET, you'll find it. And then the low sides are 4373. And this memory VRM has been fine. Like, they've been running it for ages. It's never had problems before. It's not going to have problems now. So, yeah. The neat thing is, though, that this controller right here is an APW... So, the controller they use is an APW 8722. And, okay, so the not so neat thing is, this thing is this thing is fixed voltage. So, there's no way to change the output voltage of this chip other than with a physical modification to the PCB. So that kind of sucks. The good news is because of the packaging this comes in, it's really easy to do. I mean, it has 8 pins, and you basically just put a resistor between one of the pins, you just basically need to put a resistor of the correct value between one of the pins and ground, and I've forgotten which pin. I'm not going to look it up, to get higher memory voltage, which may or may not lead to better memory overclocking. It kind of depends on what memory chips you get. I'm not maybe I don't know if Micron might not scale. It might be some memory chips might scale to stock voltage will be 1.6 or 1.5 volts. Somewhere in between those two maybe as well. But you might find that, say, I don't know because I haven't tested that many cards. The only RX 480 that I tried messing around with memory voltage on didn't scale at all. I went all the way to 1.75 volts, and the maximum memory clock stayed exactly the same. So there was no improvement. But you might find that on some cards, maybe if your memory controller is better, right? Because the memory controller is also a factor. But with a better memory controller, you might find that, if you go up to, 1.8 volts or something, you might be able to run, 2.5 gigahertz memory clock or something silly like that. It also depends on what memory chips you have. Maybe Samsung chips don't scale, or they do scale. Same could be true of Micron and also Hynix. So really, that's kind of all over the place. But if you do want to modify, mod your memory voltage, you just need to look up that data sheet, and it's actually really easy to do. I think that gives you a full data sheet. So if you just read the whole thing, you should be perfectly capable of adjusting your memory voltage. It is several pages, but come on. It's not that hard to, it's not that big a deal as far as I'm concerned. So yeah, that is the RX 590 Fatboy from XFX. I rather like it. You get I mean, it's not the most efficient 6-phase we've ever seen on an RX, like a Polaris card, right? There's been cards using, Asus has the Strix card, which uses, at least last time I've seen the Strix card, it was using IR3555s. I'm not sure if they've changed that. That's a 60 amp power stage. That's more efficient. It doesn't have the exposed drain, so ultimately it'll tend to, depending on how it's being heat synced, it might have higher operating temperatures because the thermal resistance of those chips is higher than the thermal resistance of these. But this is definitely not the most efficient 6-phase. It's still a solid 6-phase. And yeah, it's a lot better than some of the other Polaris PCBs out there. Say the one I have in my daily system, which is so bad. Anyways, that is it for the video. Thank you for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. And yeah, thanks to Tech Power Up for providing, high-res PCB pictures like this. And if you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon, and there's also t-shirts you can buy. You can find a link to all of that down in the description below. And yeah, I'll hit the stop button at this point because that's the end of the video. See ya.